So working with Corey has been extraordinarily fun. I've given him projects that I would give to a graduate student, and he's taken it with a great avarice. It's been really fun. So I think that this work is going to be an important step in understanding the evolution of the universe. So thanks very much. It's been a lot of fun.
Thank you, Dr. Collins. So my name is Corey Brummel-Smith. I've been working this summer with my professor, Dr. David Collins. I've been analyzing computer simulations that he's created of turbulent molecular clouds. So these are essentially computer simulations of star formation. Specifically, I've been looking at the magnetic fields in these simulations. The title of my talk is Magnetic Field Alignment in Simulated Molecular Clouds. So here's a brief outline of how my talk is going to go. First, I'm going to tell you about star formation and give you some background on magnetic fields. Then I'm going to talk to you a bit about computational physics simulations. And then I'll present my analysis and my results and give you a conclusion. So first off, let's talk about star formation. So stars form from enormous clouds of molecular hydrogen gas out in space. And these clouds can have a mass of 1,000,000 times the mass of the sun. So these are enormous objects, and they have enormous gravity. The gravity can pull the gas in, and the gas collapses down in on itself. As the gas falls in, it heats up, and the density increases. And once a core of this cloud gets to a high enough density and temperature, nuclear fusion is able to start in the core. And that's when it officially becomes a star. So here's a beautiful image of a molecular cloud. This is the Orion Nebula in the constellation Orion. And this is a real image taken by the Hubble Space Telescope. And there's something really interesting about this molecular cloud. And that is, it shouldn't actually be here. So what do I mean by that? Well, when astrophysicists do calculations of how long it should take for all this gas to fall in and form stars, they get an answer of around 3 million years. Now, we can actually look at some of the stars in this cloud and tell that they're older than 10 million years. So that doesn't add up. How can this cloud was supposed to collapse in 3 million years, but there's already stars that are 10 million years old? So there's obviously something else going on here. And we think that one possible answer is because of magnetic fields. So molecular clouds have magnetic fields somewhat similar to how the Earth has a magnetic field and how a refrigerator magnet has a magnetic field. But the magnetic fields in clouds are a lot more complicated, and they kind of act like rubber bands. So they're able to stretch, and they store a lot of energy, just like a rubber band. And it turns out, if the fields are strong enough, they can even prevent the gas from being able to collapse in to form a star. So why does any of this matter in the first place? Well, first off, the sun is a regular average star, and all life depends on the sun. You know, we eat the animals who eat the plants who get all their energy from the sun. And without the sun, actually, the Earth wouldn't have even been able to form. So we really depend on the sun. So understanding star formation is really key to understanding where we come from. So if we want to understand how these molecular clouds evolve, we need to find a good way to do it. And it's hard because, like I said, it takes millions of years for these clouds to collapse in. And we don't have millions of years to sit around with our telescopes looking at the sky. So we need a faster way. So how we do that is we create computer simulations of how the cloud collapses. So here's a diagram of how a computer simulation of a computational physics simulation goes. You start with your equations of physics that describe all the dynamics of the gas and how the gas evolves. And these equations contain information about the pressure, the density, the temperature, and the magnetic fields, and all of the relevant physical parameters that are relevant to the evolution of the cloud. And generally, these are really hard equations to solve. So we use computers to solve them numerically. And we can take a process that takes millions of years to happen, we can do it in a few months on thousands of processors. So this is the actual computer that some of my professor's simulations were run on, called Kraken, and it does have thousands of processors, and it still takes months to run these simulations. This is a visualization of the gas density in one of these simulations that my professor has made, and I think it's pretty neat looking. So now let me talk about my analysis. So first off, I only want to focus on the regions of really high density in the simulation because that's where future stars would be likely to form. So this here is an image of the gas density in the cloud looking along through this three-dimensional box. So I've flattened this box into a two-dimensional image, and I've outlined in red all of the high-density cores that I'm interested in looking at. And these are the regions where I'm going to analyze the magnetic fields, or where I've analyzed the magnetic fields. So the title of my talk was Magnetic Field Alignment. To measure any sort of alignment, I have to know the direction of the magnetic field. And I measured the direction of the magnetic field by the angle it makes with a horizontal axis. And I call this angle theta. And I'm interested in comparing the magnetic fields in a small region around the center of the core with the magnetic fields in a larger region that encompasses the surrounding gas. And here's what we expect. We expect to see that weaker fields get dragged along with the gas as it collapses, and we expect that stronger fields are stiffer, and that since they have more energy, they don't get tangled up as much with the gas as it becomes turbulent and collapses. So on average, we would expect to see more alignment between the magnetic fields in the core of the cloud with the magnetic fields in the surrounding gas if the magnetic fields are really strong. So here's an outline of how I did my analysis. The first step was to locate the regions of high density, and that was the regions outlined in red in that previous picture. The second step is to calculate the magnetic fields in the cores and in the surrounding gas. And then to measure the alignment, I first have to measure the direction in each of those regions and take an average of that. And then I can calculate the alignment, and I repeat this analysis for each of the cores in the simulation, and I actually do this for multiple different simulations. So I'm going to give you a specific example of how I did my analysis on one of the cores. This is the same process that I did with all of the cores. So this is another image of the density of the gas. The darker color is higher density gas. And here's the same image with the magnetic fields plotted on top. So you can see up in the top right-hand corner of this image, all the magnetic fields are horizontal. That would correspond to an angle theta of 0 degrees. Whereas in the center, the gas is swirled up, and you can see the magnetic fields curl around with the gas. So this is the small region around the center of the core that I'm looking at, and then this is the larger region that encompasses the surrounding gas. I then take the average direction in the small region and the average direction in the large region, and then the alignment between the magnetic fields at these two length scales is the angle between these vectors. Call it delta theta. So I then repeat that analysis for each one of these cores outlined in red and tally up the results. So here are my results. So there's a lot of information on this plot, and I'll break it all down. So on the horizontal axis, we have the magnetic field alignment. That's that angle delta theta between the large-scale magnetic field and the small-scale magnetic field. And on the vertical axis is the fraction of cores in a simulation that had that alignment. So there's two histograms on this plot. The one with the blue line is from a simulation with relatively weak magnetic fields, and the red line is from a simulation with relatively strong magnetic fields. They're actually about 100 times stronger than the blue line simulation. So as you can see in the red plot, the red line has a peak around 0 to 10 degrees, that means there's a lot of alignment between the small-scale magnetic field and the large-scale magnetic field. Whereas the blue line, it has a higher fraction of cores at higher delta theta, around 60 to 90 degrees. So that shows that the magnetic fields are less aligned when the magnetic fields are weaker. So in summary, more alignment with a strong magnetic field and less alignment with a weak magnetic field. So, in conclusion, can we say that stronger magnetic fields produce more alignment? This histogram suggests so, but there's one thing I left out, and that is this is just looking along through the simulation box along one line of sight. So, for instance, this is the y-axis. I could also look along the x-axis or the z-axis, and when I did that, we actually didn't find the exact same results. So we think that there must be a better way to do the analysis, to measure the bending and the alignment of the magnetic fields. And I'm currently working on a much better, more robust way to analyze the alignment in the magnetic fields, and we think that it'll give us much better results and in the future could be very helpful for astronomy. So how this relates back to initially what I was saying about star formation is it's really hard to measure magnetic fields, or it's very hard to measure magnetic field strength. So if we were able to find a strong correlation between the alignment of the magnetic fields and the field strength, this might help us identify the magnetic field strength in real molecular clouds out in space. So thank you for coming here. I would like to first thank Dr. Collins for supporting me with this research. His help and guidance has been invaluable, and I can't thank you enough. I'd also like to thank everyone at the Center for Undergraduate Research and Academic Engagement. They were the ones who provided me with the $4,000 to do this research. So I'm very thankful for the IDEA grant and their support. So, does anyone have any questions? Question? Yep.
So, not being a physicist, I sort of associate magnetic field with like the picture you showed, a mass, like the Earth or a magnet. These are magnetic fields that just exist in space, or is it they're there because the cloud is there? In other words, are there fields where there aren't clouds too?
So, in general, magnetic fields arise when you have charged particles that are moving with some velocity. So while these clouds are actually pretty cold and the hydrogen is not charged, there are regions in space where there's really hot gas that is ionized, which it means they're charged particles and they're moving really fast. So for instance, in a supernova explosion, that can create really strong magnetic fields. So I'm not clear exactly on the origin of all the magnetic fields, but I know that they arise from moving charged particles. Yep.
At the moment, can the simulator only simulate completely random molecular clouds, or can you take ones that are actually in space right now and put it into the simulator and research it?
Great question. So these simulations aren't using real data from telescope observations. They're just based on the equations that govern the dynamics of the cloud. So you start with some initial big box full of gas, and you mix it up so it becomes turbulent, and then you just watch what happens as it collapses. So to answer your question, no, you don't actually use telescope observations or real data to feed into the simulations. And as far as I know, the code that Dr. Collins has used to create these simulations doesn't really allow for that, but I don't know if there might be other codes where you can do that. Any other questions? Mallory?
You said that the computers run thousands of processors to create
That's right.
Whatever, how does that work?
So it's called parallel processing. It's a really interesting way to solve problems. So a simple explanation of parallel processing is, say you want to add 4 numbers together, 1 plus 2 plus 3 plus 4. A normal computer would do it by adding 1 plus 2 and then plus 3 and then plus 4. With parallel processing, you break the job up into separate parts. So you have one processor run 1 plus 2, and then the other processor run 3 plus 4, and you do it in half the time. So you multiply that by 1,000, you can do what would take, you can cut the time in 1,000th.
Kind of a speculative question, but what do you think that the implications of it only being a stronger field for a smaller angle is from being only on one axis?
I'll talk with you more about this. We're actually out of time, but I'll discuss it with you after. So thank you all for coming.